tape. All right, so we're taping. So we've officially begun. The lighting situation appears to improve. It hasn't switched off yet, so um, let's hope that uh, keeps working. Um, so one of our homeworks has disappeared, right? The one that was due last Wednesday from this list. So that's good. But I added one more today. We'll start talking about this operation with vectors, which is called dot product, which is a very simple operation to execute. But it doesn't have an analog for numbers. So this is an operation that's unique to vectors, right? Okay. So we add vectors together, right? And we multiplied vectors times scalars, real numbers. But those are sort of similar to the things that we do with just numbers, right? With real numbers, in the vector context called scalars. But dot products is kind of unique to vectors, and it's one of two really important unique operations that we perform with vectors that don't have similar corresponding operations in just for real numbers, for scalars. So anyway, I added this homework, and I think that if we do pretty well today, I think you can start on this, but probably the last couple of problems, which are physics problems, well, we probably won't be able to finish those because I don't think we're going to get to that physics example today. That is similar to these. Actually, we may get to an example, but these are a little bit more complicated. The homework problems are a little bit more complicated than the example, so you may not be able to finish those before next time or over the weekend. Anyway, this is not due till next Wednesday, and so now the first homework on space coordinates. We're still not through talking about that, so I moved that back to Monday. So it's not really due tonight. It was originally due tonight, but I moved that back till Monday so we could finish talking about this. I don't think it's a terrible homework, but we didn't finish talking about it. So that's the homework list. Let's see, what was I going to say? So the first homework, everyone worked on that, and the average was high. So that's good. I didn't look score by score at everyone's score, but the overall class average was really high. So that's good. So keep that up, right? Okay. And but if you didn't have a high score, right. So try to improve that on your next homework. But again, remember, you can request an extension, right, when you run past the due date. But you won't be able to request that now on the prior homework because it's a little bit too late now for the automatic extension. You have like a 2-day window to ask for the extension. But keep that in mind for this homework if you don't finish it. But we still have till Monday, right? Okay. Keep in mind, I mentioned last week I am in the center from 2 to 5 on Mondays and Wednesdays afternoon, but I sometimes have appointments, and so I get booked up. But and so I'm not really freely available. Like today, I have appointments all afternoon. Now, sometimes those appointments don't end up lasting very long, but so I do have some free time, but it's hard to predict. But on the other hand, I am so you can make an appointment with me in the Math Center on Monday afternoon yourself if you want to come see me. Just go to this Math Center page. Where is that? Right here. Yeah. Okay. Go to this link and you can make an appointment. You have to follow the instructions there. They're a little bit convoluted, but follow the instructions there to make an appointment with me, or you can just come see me in my office before class. So I'm usually in the office until about 11 before class, which is South 611. Is that on? No, I did not list that. Okay, but my office is South 611, so I need to add that to this announcement about office hours. But South 611, maybe that's on the syllabus. Okay. Well, anyway, all right. So that's kind of just general stuff there before we start the notes. Y'all have questions? What day in the syllabus is the test listed as? So uh February 21? Can't be January 21, right? So I mean can't be August or September 21, right? I'm thinking in spring. September 21. What is today? The 5th, 6th, 7th? Ooh, so that's 2 weeks. Oh boy. Okay. So all right. So that means we need to have a sample test. So I'll have to work on that this weekend so y'all can see that. All right. Before that test date. If we have to push the test back till the following Monday, that's not I think is the 20, what do you say first? That must be a Wednesday, right? That's 2 weeks from today. So then the 26th would be the following Monday. If we have to push it back to there, that's okay. We'll just have to see. All right, where we're at. All right. But I will be working on the sample test then. All right, I'm going to give you here again some graph paper, but I've drawn on this one. So I've drawn some three-dimensional axes on here, but I have not labeled them because you're going to label them, and then we're going to draw some vectors. But I didn't want to spend a lot of time. I didn't want you to spend a lot of time actually drawing the axes themselves, but you will have to label them, right? Okay. When we get to a point where we're going to do that. So just hang on to that for a minute. We have to do a lot of this drawing to get ourselves accustomed to 3 dimensions and sort of thinking freely in 3 dimensions, but that will take a little while. All right, so I'm gonna do y'all have questions? Because I'm gonna start the notes, which is really just resuming with where we were at in the notes, where we're at in the notes last time, and we'll see how much we can get done on this holiday shortened week, right? So we got one day this week, and then we're off again until Monday. So which is nice, but at the same time, that squeezes us for a little bit for time here, right? So any big questions there? I hope you haven't forgotten everything already over your holiday. So, but that's okay. It's not really that much to remember so far, right? All right. So let me lower this screen so I can write a little bit easier. All right, so remember we're working in 3-dimensional space right now. So we have it's still Cartesian 3-dimensional space, right? So we have these instead of 2 now, we have these 3 sort of orthogonal axes, right? And we're using those axes to locate points in 3 dimensions, right? Instead of on a plane, right? In 3-dimensional space. And just like with 2 dimensions, right? We can create vectors in 3 dimensions as well. Okay. And vectors in 3 dimensions work just very similarly to vectors in 2 dimensions, right? Okay. So in 3 dimensions, though, right, a vector has an initial point which has 3 coordinates and a terminal point which has 3 coordinates as well, right? Okay. And the initial and the terminal point are important, right? Because that implies the direction of the vector, right? So, of course, vectors in 3-dimensional space have a direction, and they also have a magnitude, right? Okay, and that is computed using the 3-dimensional analog of the distance formula, which is just similar to the two-dimensional distance formula, right? Except you have just a third term under that square root, right? That's part of the distance formula, and that's the difference in the third coordinates, right? Of your three-dimensional points, right? That's the difference in the third coordinate squared, right? That you insert also under the square root, right? In the three-dimensional distance formula. Now you can take these three-dimensional vectors and you can put them in component form, what's called component form, by assuming that the initial point of the vector is the origin, which has coordinates 0, 0, 0. All right, so just like with 2D vectors, we can put 3D vectors in component form. And when we do that, when we have a 3D vector in component form, right, we enclose it in the pointy brackets, right, just like we do with a 2D vector. So a 3D vector just has that third component, right? Okay, as part of its component representation. And just like with 2D vectors, you can take 3D vectors and you can write them as a linear combination of 3 unit vectors, right? Okay, the 3 unit vectors is the unit vector along the x-axis in the positive direction, the unit vector along the y-axis in the positive direction. Those are referred to as I and j again, just like they are in 2 dimensions. But in 3 dimensions, we also have a unit vector. We can also define a unit vector along the z-axis, right? Which usually we draw vertically when we're plotting in 3 dimensions along the z-axis, also in the positive direction. That unit vector, vector of length 1, right, is a unit vector. That vector is referred to as usually as k. It's labeled k. All right, so the vertical unit vector, and then you can take any vector that's in component form and you can rewrite it as a combination of, right, these 3 standard unit vectors. And this is called standard form versus component form, but it's essentially the same as component form. So keep in mind that vector I is, right, the unit vector along the x-axis, right? So its component form is 1, 0, 0, right? 1 on the x-axis, 0 on the y, 0 on the z, right? The j unit vector, that's 1 unit along the y-axis, right? So 0 along the x and 0 along the z-axis. And then here's the new unit vector called k, right? Which is 1 unit along the z-axis, 0 on x and 0 on y. So there's a picture in 3 dimensions drawn by the book, so it looks all beautiful, right? There's a picture in 3 dimensions, right, of there's the I unit vector, there's the j unit vector. This is the y-axis in this picture here. This is the x-axis in this picture. And then, of course, usually vertically is the z-axis. There's the k unit vector. And then again, you can take any vector and write it, again, as a combination of a sum of these 3 unit vectors, right? Okay, so see, vectors in 3 dimensions look like vectors in 2 dimensions, except you got 3 dimensions, right? Okay, so they're not going to be as easy to plot, right? They're not as easy to graph, unfortunately, as they are in 2 dimensions, because you have all of these problems with plotting in 3 dimensions, right? That you don't have in 2 dimensions. Well, so far, so good, right? And actually now, lots of other things, right, are the same for vectors in 3 dimensions as they are in 2 dimensions, right? Okay, so there's putting the vector in component form, right? You simply, if you have the initial and the terminal points for the vector, right, you simply take the difference, right, of the coordinates, right? Terminal point minus initial point, and that gives you the vector in component form. So remember, component form just means that just is the assumption that the initial point of the vector is at 0, 0, 0, right, which is the origin for a 3-dimensional space. If you have a vector in component form, it's easy to compute its magnitude or its length, right? You just take the sums of the squares of the components and then take the square root of that, right? So there's how you compute the magnitude of a vector, and that's kind of the length of the vector geometrically. although in applications, the magnitude of the vector sometimes means something else other than just the length of the vector, right? If you want to take a vector and cut it down to a unit vector, right, you just divide it by its magnitude. And that gives you a vector in the same direction as the original vector, except this new vector has length 1. Okay. Sometimes this is called normalizing the vector. All right. So taking it and giving it dividing it by magnitude, that gives you a new vector, but its length is 1. But the new vector has the same direction as the original vector does. Of course, you can add vectors together, right? And just like in 3 dimensions, just like you do in 2 dimensions, and you can multiply a vector by a real number, a scalar, in 3 dimensions, just like you do in 2 dimensions, right? Just by taking the scalar, the number, and multiplying it by each of the components of the vector, right? So remember, this is scalar multiplication, right? This is a number times the vector, and they're trying to distinguish between the number and the vector, right? By they're putting the vector in bold, and they're leaving the number in italics because they're trying to make it clear to you that these are not the same sort of creatures, right? This is a number, and this is a vector. And that's going to become important because a little bit later on, we are going to see expressions like this, okay, where you have 2 vectors written side by side, and so we need to distinguish this expression from this type of expression, and what's happening here from this type of expression, right? Okay, but not quite there yet. But soon we will be. Okay. All right. So far, kind of not interesting, right? or not that shocking, right? Vectors in 3 dimensions. So let's practice a little bit just with this idea. So here we have a vector that has, I think this vector is called V. I kind of squeezed the V in there. So we have this vector V. It has initial point -2, 4, and 1, and its terminal point is 0, -4, and 2. Okay, so here you're given the initial point and the terminal point. And now what we want to do here is find the magnitude of this vector, right? And then also the unit vector that has the same direction as V, because I don't think this vector that's described here has magnitude 1. If it did, it would already be a unit vector. But we want to find then the unit vector that is kind of similar to V, right? It has the same direction as V, but just has length 1 instead of whatever the length of V is. Now, just to make this more fun, because this is all kind of this is all just kind of arithmetic, right? So to make this more fun, though, let's actually draw a picture of these vectors. So that's what I gave you the axes for, right? So as a little bit of recall practice here from what we were doing last time, let's draw a set of axes. So use the first set of axes that I gave you on the graph paper, right? The one on top. I want you to label those. So label the axes. Of course, the vertical axis is going to be Z, so that's kind of a giveaway, right? But how would we label the other 2 axes? Those are going to be X and Y. So which one would be X and which one would be Y? Then how would the numbers be put on there on the tick marks, right? Because I already put the tick marks on there. How would you number the tick marks? So that you have a quadrant 4 perspective, okay? A quadrant 4 perspective. So how would you label the axes? And how would you number the tick marks on the axes, right? So that you appear to be looking at that set of axes from the 4th quadrant. So you're sort of hovering above the 4th quadrant, looking at looking sort of down on that set of I guess could be, well, it could be up, but let's concentrate on looking down at that set of axes, right? See if you can do that. And then once you've done that, try to plot the original. So try to plot that vector, the original vector that starts at this point and goes to this point. So you're going to have to try to plot these 2 points and then, draw a vector between the 2 points. And then also plot the same vector in component form. Plot the same vector in component form. Shall we write down the vector in component form so you'll know what to plot? Because this vector is not written in component form, right? So let's try doing that just so I'll get you started here, right? So what would this vector v look like in component form, where we assume that 0, 0, 0 is the initial point? See here, the initial point is minus 2, 4, and 1. So if we take this vector and translate it down to the origin so that the initial point is on the origin, what is that vector? Well, remember, you get that just by taking the difference in the components, right? So you would have 0, here's the terminal point, minus a minus 2. That's going to be the x component. And then minus 4 minus 4. Am I doing that right? Yeah, that's going to be the y component. And then 2 minus 1. Ooh, that y component's really big. So I hope I put enough. You may have to add some tick marks there to your axes. So what is this? 2 minus 8 and 1. Is that right? Did I do that arithmetic right? Zero minus a minus 2, minus 4, minus 4, and then 2 minus 1. Yeah, I think I did the arithmetic right. So there's the vector v in component form. So you're going to graph two vectors, the original vector v, and then the vector v shifted, down to the origin. So in other words, graph this vector. That's a big y coordinate though, so I might not have put enough y axes there. You may have to extend your whatever you label y axes and put it or take. So try to check that. So this is the so so split. So maybe split. Say you're sort of flat. That I will add to extension by axis of found in. So I see. See. Exactly. Oh, I see.
Oh, I see. Two, two. Yeah, I think that would be see. Sort of. So try to keep Z vertical just to keep our sanity always working. So how would you label those? Down, sort of. And some numbers. Yeah, really have to sort of that you really have to act. So so what was the this is the point. Remember you're always starting to so better. Then you think so it's but yeah, something around there, it's hard. And then you have to just sort of imagine that, looking at that vector. So yeah, I see. You just assume this is negative. Or quadrant. We're plotting two forms, right? Original form and then the component form. They all end up with vectors. You look, do it right, and you look at it just right. Those two vectors should say should right, your visual imagination is not good. Right. Oh, sorry. This is good. So you probably uh, so that term. What's the initial original initial point. Oh, well, that's in component. Okay, but I also said, how do- let's do it again. So we want to go two, four, seven, eight, two, four. So the picture, right, blue lines, okay, right there, and up one. Now up one is really up, but uh, but fortunately, nice somehow. Looks like this is vector. Actually, got those right. Got the dot points there. So you got two jobs here: plotted original. So that's connecting two points vector. And plotted. Right. Two. But see, plotting points there is having fun with that. That is a hard thing to do. Right. So what? So this is the x-axis. So how are your tips? Like, yeah, you did. Is it minus one? This way, plus this way. So this is two. Supposed to be one. Or above this. From sort of yourself. That section has that's negative. X. So you got a label in it. Um, it has a copy to let's find it. So you put a two, two. So now it's picking it up. That's what's really good. But so that's so but but see I'm looking at this, right? So you're thinking better. That's right. Yeah, so that's the third mission. Looking at accurate. So sometimes you can use it. Yeah, right. Right. Okay. So right. Two, say, see. would start at two. Sorry. Hey. But it looks like that. That's what. So. Next. Third. I want. Fix this just. All right, so that looks nice. I can almost actually see that price. So component forms are so which is X, this is X. So this is positive. This is negative. So, so C2 on X and so lower straight parallel. So 2 minus 1 is C minus 8. Take marks are say so I'm on it. That's cool. Thanks. Oh, yeah, okay, so y'all are doing really good. So that helps me a lot understand. Let me see if I can see if we can scratch this in really. Let me switch to the document camera. Try not to bust things here. This document camera is not stationary. Wow. And cannot be able to do this very well. All right, so there were really a couple of ways, right? You could have there were really a couple of ways, right? You could have there were really a couple of ways you could have plotted things. But I would have probably started by putting labeling this as the x-axis and labeling this as the y-axis and this as the positive side. This is the positive side of the x-axis and this is the negative side of the y-axis. Okay, because in the in the fourth quadrant, right? X is positive and Y is negative. So if we see this as being the fourth quadrant and we're above the fourth quadrant, then if we have Y is negative and X is positive, that would be the right location, right? Now let's see if we can, what were those points though? What were those points though that we were trying to, in the original form of the vector, what were those points that we were trying to plot? Let's see, what was the original initial point for that vector V? Okay, so let's see if we can find that point and try to plot it. But remember, we have to use our visual imagination a little bit, right? Because we're working in 2 dimensions, but this is really a point in 3 dimensions, right? So we have to be a little bit flexible. So we said what? X was what? -2. That would be if this is, if we're going by 2s on the tick marks, which would, or you could have gone by 1s, but let's just assume we're going by 2s on the tick mark. So there's -2, and then Y is what? 4, which is up here. So look, make sure you're going parallel to the y-axis though, right? Up 4. So this would be 4, right? So go up. So you're right here. If you're on the XY plane, you're right here. But we're not on the XY plane, right? We are, is it above the XY plane? Because we're at Z equal what? 1. So we have to pretend that we're coming up 1. Well, you know, we really can't go up 1, right? So visually, we would picture that by going up on the Z axis, right? So I think that first point we could put right here, right? Okay, or something like this, right? Or maybe I did I get that in the right spot. Yeah. Okay. So see, that point is hovering above -2, 4. Here's -2, 4 on the XY plane, but we're above that, right? Okay, so this point is really supposed to be above the plane, but of course we can't draw it above the plane, right? We have to just kind of think it in the picture. So we have to kind of imagine that this point is above the plane. So now the book adds sometimes some kind of visual clues, right, to help you understand that you're really above the plane, but that means we have to add a lot into the picture. So I'm going to try to avoid that there. So there's my first point. What was the second point? X0. Yay. Okay. And then what? -4 down here. And then what? 2 up. So see, that looks like we're right on the x-axis, but we're not, right? Okay, because we're looking down, this point is obscuring the x-axis, right? We're looking down on this point, okay? So it's obscuring the x-axis, so we can't see this part of the x-axis, but that's because we're above the x-axis looking down. This point is really not on the x-axis, right? It's really above the xy plane, right? And then just connect those with that vector, right? Well, you know, there you go. All right. You see it very well here? That's not great. Okay. That's what it looks like. Now, what does it look like in component form? Seemed like it was much longer in component form. So what was it in component form? 2. Is that the right points? Did we do that right? That looks. Oh, I went by 2s. Yeah. Okay. Yeah. All right. So we're at what? 2 on X, right? -8, which is down here, right? And then what? Up 1, maybe right there. So there's the vector in component form. Well, not bad, right? They do sort of look at least parallel, which they're certainly supposed to be, right? Okay. But this one maybe is a little bit easier to imagine starting at the right, and it's a little bit easier to imagine that it's coming up off the plane by. Okay. This one is
That one's a little bit hard to see because it's, what is it, going up from 1 to 2 or something? So it does have an elevation of 1. It's really hard to draw that. Show you something like that. Now, you may have labeled the axes differently, right? Okay, so it is possible to label the axes differently so that you're still getting a fourth quadrant view. What would that be if you switch x and y? Right, so if you make this y and make this one x, then how would the this would have to be what, positive x? Is that right? And negative y here, yeah, and that still would perspective. Okay, so but then your picture might. Is that struggle? Was that hard? Do that. Hang on a minute. All right, let's I'll show you something that might, if I can find my mouse. There it is. Let's scroll up a little bit. I forgot the other part of this problem. So what else did we want to do here? Just find the what? The magnitude of V. So in component form, that's real easy, right? In component form, the magnitude of V is just the square root of the sums of the squares of the components. So you would have 2 squared plus the minus 8 squared plus the 1 squared, right? What does that work out to be? Square root of, is that 69? Am I computing right? Which is not a prime number, but you're not going to be able to simplify by hand square root of 69. That's 3 times 23, and 23 is a prime number. So I just have to leave it like that unless you want a decimal approximation. And then how do you get a unit vector in the same direction as V? A unit vector in the same direction as V. Divide by the magnitude, right? So you would have your unit vector in the same direction as V would be V over the magnitude of V, right? Which is going to be, just take all of those components, right? And divide them by square root of 69. So if we put that in standard form, that would be 2 over square root of 69 times I minus 8 over square root of 69 times J plus 1 over square root of 69 times K. Here it is in component form, right? So I just took all the components. Oops, I'm writing there and y'all cannot see. Stop me, right? Like that. Yeah, okay, so there's the magnitude, right? And then just take all of the components and divide by the magnitude, right? And if you want to write it in standard form, which is a combination of the ij's and k's, right? Here's what it would look like. Standard. So if you draw a picture of that vector, if you draw a picture of that unit vector, what would that look like? Well, it would look like this one, right? Because there's the component form of V, except it would just be shortened, right? Until it has length 1. So you would just get a shorter version of this vector, right? Vector of length 1. Okay, now hang on to your graph paper because we're going to label this one, but we want this, we're going to label this one from quadrant 1 perspective, but not yet. Okay, so so we're going to switch back to the quadrant 1 perspective for the second one because we're going to do some more drawing there in a minute. Oh, I want to show you something now. Let's see if we can get this. Let's see if we can get the computer to do some graphing for us. So I'm going to switch here and go to this program called Wolfram Alpha, which is just wolframalpha.com. So if you've ever seen Wolfram Alpha, this is called the computational engine. And it does tons and tons of things. Yeah, I'm still on now. Wrong thing. I have a link to this in all of your assignments.
at the top, either where it's got directions or instructions at the top of your homework. Um, I think I included a link to Wolfram Alpha. And the nice thing about Wolfram Alpha is it tries to use natural language. So you can sort of type in what you want done, kind of in the way you're thinking of it in English, and then you can see what Wolfram Alpha does. And sometimes that works nicely, and sometimes it doesn't. Now, the bad thing about Wolfram Alpha, however, it's got this, because this is the free version that's available on the webpage. It's got this command line interface, right? So you have to literally type in commands. For you guys that aren't as old as me, using command line interface like this is probably seems a little bit clumsy. Well, it is clumsy, okay? But this is the way we used to do things. All right, so let's try plotting. Let's try plotting those 2 points. Let's try plotting those 2 points that were the initial and terminal points of that vector. I don't know how to get the vector between those 2 points, but I do know how to get the vector in component form, I think. So we'll plot that also and see what it looks like in Wolfram Alpha. And this could help you sometimes when you're doing your homework, because the homework is not going to ask you to plot vectors, or points, but it will tell you to plot a point and then say which of these is the correct plot. So if you can't figure it out just from looking at the graphs, which probably you can try cheating here and using Wolfram Alpha also and see if that's helpful. So let's see if we try plotting. Let me just use the command plot here, and see if I can remember how to do this. And I think you have to tell Wolfram Alpha that you want to plot a point. All right. And then let's put the point in, I'm going to put the point in curly braces if I can find the curly braces on here. But if I can't, we'll just try using parentheses. Do y'all see the curly braces? Huh? Oh, right here? Yeah. So oftentimes Wolfram Alpha will use curly braces instead of parentheses for things. But maybe the parentheses would have worked also just as good. I don't know. Maybe this won't work. So what was the first point? The first point? No, just the initial and terminal points. So -2 and then something, what? 4 and 1. All right, so let's close that, and then let's try and then let's tell it again that we're plotting a second point here. And what was that second point? 0, -2. 0, -4, and 2. All right, let's see how things work here. And then we just hit enter, or you can hit equal here. Let's see if Wolfram Alpha is going to be nice to me. So did it do something? Yes. And so there's its picture of the there's its picture of the 2 points. Let's see if we can make sense of that. What quadrant are we? See, this is the negative side of the x-axis. Over here is the positive side of the x-axis, right? There's the negative and positive side of the y-axis. So that's looking down, I think, from the first quadrant. Okay, we're sort of positioned up here, right? And so that's this is positive side of the x-axis. They didn't extend this, but this is the positive side of the x-axis, right? And then here, here's the I see. Okay, so down from the fourth quadrant again, positive side, and then negative side of the y-axis. Yeah, I think that is from the quadrant, right? Okay, so we are indeed in the fourth quadrant, and
Well, here's their 2 points. It kind of looks like the 2 points that are a picture. And so you can imagine they're connecting those with a vector. Do you get, does the box help sort of, box help with the elevation of the points? I think it does, okay? It does give the impression that this point is above this one, right? Okay, so I do see that a little bit, and that was what we were discussing, right? With our picture, had trouble indicating, right? The second point is higher than that. Maybe I should have done some better job of picturing that. Now let's look at the vector in component form. Let's look at the vector in component form, and that's also pretty easy, I think, to plot. Just put plot, except I think it helps, but it may not be necessary. But tell Wolfram Alpha that you're interested in plotting a vector. Okay, so you want to plot a vector, and let's type it in standard form. So what was the standard form for that? Standard form. So that means as a combination of I, J, and K. So what was it? 2I. And then what, minus something? Minus 8. Minus 8J. And then plus, was it 1? It only had like an elevation of 1, right? So plus, where's plus on here? Plus K, 1K. So just plus K. Let's see if it knows that. Looks like it didn't complain about that at all. Oh, so there is, there's their picture of that vector. So I do see that vector rising. And wow, where are we? So that's X, right? So it's like we're on the positive side of X, and then I okay. Yes, and then what over here in the negative side of I, right? That's like first one. And yes, I think we're sort of down there from the first quadrant, right? That's what it looks like. Is that vector going into the first quadrant? Oh, it was going into the fourth. Starting. That so is that a negative y-axis? That's drawn. I mean, the vector is obviously drawn correctly. You know where. So think of this line up here, labeled this line. That's the positive side of the x-axis, right? Negative side. That is. So it's going into the side. It's easier to think of 0, 1, 2 as being. But 0. All right, so you do have some tools here to plot vectors and things. One thing you don't want to do with, and so you just tell Wolfram Alpha plot pointer, plot vector. It may take the points in parentheses too. I don't know if you need the curly braces. I think it's friendlier if you put the vector in standard form, right? It's easier to plot, but you cannot get carried away. So it's not going to plot like I tried plotting more than 2 vectors. It doesn't like that. Okay.
So it's kind of limited in that sense. I'm sure there is a way of getting it to plot more than two vectors, but this simple-minded way of just putting plot vector won't do it. If you want to plot two vectors, put a comma and then repeat the word vector. Okay, so repeat the word vector and then the vector in standard form. It just separates your vectors with a comma, but you do have to repeat the word vector. Okay. Let's keep going there. All right, let's see if we can answer this question, but I didn't mention the box. Okay, so the box is important. Two vectors are parallel. This kind of makes sense, right? Two vectors are parallel, and one of them is a scalar multiple of the other. Okay, so if you've got two vectors and you can multiply one of them by a scalar, a number, to get the other vector, then you know those two vectors are parallel to one, right? The scalar can be negative, so don't forget the scalar can be negative. You can have vectors pointing in opposite directions, and you can still consider them parallel. Okay, vectors don't have to be pointing in the same direction to be parallel. So let's answer this question quickly because it's pretty easy. Suppose you have a vector and it has initial points as given, right? Initial and terminal points as given. And then the question is, which vector is parallel to W? Okay. So there they give you two vectors in component form, and they want to know which one of those is parallel to W there. Okay. Let's put W in then. Let's put W in component form, right? It's very hard to work with vectors if they're in, this original initial terminal point description, right? So let's take W and let's put it in component form. And that's so easy, right? You just take the difference in the components, correct? So you get -4 minus 2, is that -6, right? And then you get 7 minus a -1, is that 8? And then 5 minus 3 is 2. Did I do that right? So don't let me make a mistake or we'll never find our mistake. -4 minus 2 is -6. 7 minus a -1 is +8, right? And then 5 minus 3 is 2. So there's the vector W. Okay. Oh, I just can't stand it. Let's look in. Did I close WebAssign? Let's look in WebAssign at let's plot these vectors. I just want to see if we can answer our question that way. All right. So let's plot those. Let's plot that original vector W, and then let's plot one of the other two vectors that we were given. So what's the vector W? What was it? Something I. -6i. So -6i, and then plus 8j, and then plus 2k. So did I get that entered right? And then let's just put a comma there, and then let's type vector again, and then vector. And then let's try one of those other vectors in standard form. So what's the first one that's given to us there that we were checking? Did y'all get a chance to write that down? Let's look. So we wanted to check this vector U. All right, so that's 3i minus 4j minus k, right? So 3i minus 4j minus k. Let me see if I can remember that long enough to type it. 3i minus 4j minus k minus k. All right, so and then you can hit enter here or here equal, and let's see if it'll plot those two vectors. Just praying here that it does. So it did, and wow, okay. What are we really looking at there? yeah, that's right. You're looking at two vectors going in opposite directions, right? So we can check to see which one is we can study the graph here a little bit, right? We can check to see which one is the original, which one is U, right? Okay, but those are going in opposite directions. Now, it could be an illusion, a spatial illusion, but they certainly do appear to be what? Magnets. Of different, I don't know if they're different magnets. I don't know where each stuff. Oh, I see. 0, 0 right there, right? Like right. Zeros. So yeah, one. There's, okay, and but they do look like they're parallel, right? Okay, they just appear to be going in opposite directions, but parallel. This looks like just one long straight line, right? Okay, that would parallel. Parallel vectors don't have the same direction. They can be going in opposite directions. Now, that could be a spatial illusion because if you were, say, you had two vectors that were not parallel to one, they formed an angle. But if you were looking at them directly down like this, they would be directly down onward, right? They would appear to be parallel. Right? You couldn't see the angle between them right now. So maybe that's just an illusion, but it looks like they are indeed looks like they are parallel, right? But we don't have to depend on our eyesight, right? Because all we have to do is check to see if this vector and this vector are scalar multiples of one another. And I think they are, because if you take u and multiply it by what would give you w. So w is equal to what scalar could you multiply by u to get -2, right? Yeah, just multiply each of those components by -2, multiply each of these components by -2, right? And that would give w. So w is -2 times u. So indeed, see, they are in opposite directions. And David, your intuition was exactly right. -2 is going to have, I'm sorry, w is going to have twice the magnitude of u. So w was longer there, right? Okay, but and in a different direction from u. Is this true for v as well? So can you get a w as a multiple of v? So is it something here times is it something there times v? Let's see, what would it have to be to get to multiply v and then get w, which is here, right? I'm pointing to the wrong thing. To get v and then to get w, you would have to multiply by what, -1/2? Is that right? Because -1/2 times 12 is -6. So does that work for the other components? -1/2 times 16 is +8, right? And -1/2 times 4 though is -2, right? So oops, didn't quite work, right? So this answer is false. I don't think there's anything you can multiply by v to get w, because it would have to be -1/2, but that doesn't quite work. So when we plot these two vectors, they're not going to be parallel, right? Let's take a look. So 12i. So let's plot that second vector, if I can do this right. So it's what, 12i and then -16. So 16 and then what was the k? Plus 4k. Whoops. Plus 4k. And yep, not see, definitely not parallel, right? Okay. Because you can see that nice this one kind of funny. Let's just to distinguish. So anyway, these vectors see out there between the top. So that does raise the question, going to take up shortly, and that is, how do we the angle between two vectors? And so the vectors are not parallel. First, if they're parallel, the angle between 0, 180, right? Okay, but two are not parallel. So, just that. We want to know that at some point. Okay, this one is, I think, kind of not that interesting. But so here's the question. It says, determine if these points, so we're not going to plot the points, but determine if these points, without plotting them, right? These three-dimensional points, determine if they are collinear. So do they fall on us? All fall on a line. All right. So if you plot all of them, all fall on the same straight line. Any suggestions of how to answer that one?
Start with paired against the two. Paired.
Okay, so form a vector there between the points P and Q, right? I think we can denote that this way. So this vector from P to Q with this as initial point and this as terminal point, right? Okay, and so let's put that in component form though. So that vector from P to Q. So just take a difference of the points, right? So we have 2 minus 1 there is, we have 2 minus 1 there is 1. And then 1 minus a minus 2 is 3, right? And 0 minus 3 is negative 3, correct? So there's the vector from P to Q. And now, David, you said also try what? Do PR? And so that's also easy to calculate, right? That's going to be 4 minus 1 is 3. 7 minus a minus 2 is 9, right? Minus 6 minus 3 is minus 9. And then what question there you just tried to answer?
If they're just not.
Yeah, meaning that those vectors would be what? Yeah. Yeah, points are collinear, but vectors are begins with a P, parallel, right? Okay, so we just want to check, are these two vectors parallel, right? See, think about it in space, right? If the vector from, let's think of this is P and this is Q, right? So I don't know where these are hanging around in space, right? But if the vector from P to Q, right, is parallel to the vector from P to R, right, then I think those points have to all fall on a straight line. Okay. Keep in mind R might be down here though, right? Okay. But still, if the vector from P to Q is parallel to the vector from P to R, then those points all have to fall on a straight line. Is that true? So to check if they're parallel, right, you're just going to see, is one of these a multiple of the other, right? So so is there something we can multiply by PQ in order to get, so is there something I can multiply by PQ in order to get the vector PR3? So is that the case? Can we just check that? Yeah, that's true, right? Okay, we don't even have to write that down. That's easily see that eventually. 3 times see. So indeed, those points all fall straight line. So another big task for us now is how do lines in space look like? Not geometrically, right? Because a line in space looks like a line on the plane. Okay, it's a line. But what I mean is algebraically, what does it look like? What is the equation for a line in three-dimensional space look like? Okay. How do we write down an algebraic equation that defines a line in three-dimensional space? That's going to turn out to be easier said than done. It's very easy in 2 dimensions, but doesn't have to be that simple in 3 dimensions. Okay, now this last example is important. Okay, so let's take a few minutes because we have to rev up for this one. All right, so let's take 5 minutes or so and take a break so that we can do this this example, because this one involves physics, and so that always gets a little bit that's out of our comfort zone, right? So we have to think about this a little bit. All right, so I've resumed the recording. So let's start here again. And so pay really close attention to this example, because the last 2 homework problems from this current homework, I think resemble this problem, but actually they're a little bit harder than this problem. So if you're going to have any hope of doing those, you're going to have to understand this one. And even that may not be enough. So we'll talk about those problems next time. That's one reason I moved the homework due date back. All right. So okay. So we've got but the setup here is very simple. So you've got a TV camera. Now this problem is a little bit archaic, because that is a heavy TV camera, 120 pounds. But anyway, the weight there is kind of not important, right? So you've got a TV camera that's mounted on a tripod, right? As shown here. Now they have conveniently situated that tripod in 3-dimensional space, right? Okay, to make it easy to think about, make it easier to think about the problem. And so what we want to know though is so obviously, right, there's a downward force, right, being exerted on the tripod, correct? Because the tripod has to hold the camera, right? The camera is gravity is pulling the camera down, right? With a force of 120 pounds. Okay. And but of course that weight is really being distributed across the weight is really being distributed across the legs of the tripods, right? Okay, so each of the tripods legs do not have to be able to support the full 120 pounds, correct? Of force. So kind of the question is, well, how much force really is on each leg of the tripod? Now, the tripod is nice and symmetric. It's a tripod. So the weight of the camera is being distributed equally amongst the 3 legs, right? But so maybe your initial reaction is that means that each tripod leg is supporting 40 pounds. Okay, but that's going to be incorrect. Okay, and that is because the force, right, on the tripod leg is not directed straight down, vertically down, correct? So that changes the force on the tripod leg. All right, now look, however, you are correct. Gravity is indeed pulling the camera straight down. All right, that's the way gravity works, right? So the camera's being pulled straight down with a force of 120, with a force there of 120 pounds. Okay, all right, so let's write a vector that represents the weight of the tripod. Okay, so in other words, I want to write a vector that represents the gravity force on the tripod. Okay, not I'm sorry, on the that's acting on the camera, that's pulling the camera down, not the forces on the individual legs of the tripod. Okay, we'll get to that. All right, so let's call that's kind of the big vector here. So let's call that F for force, but this is the gravity force vector, just the gravity that's working directly on the camera. All right, so I want to call that that. What is the direction of that force? How does gravity work? It's going what? Straight down. That's right. Okay. So that vector F is pointing straight down. Okay. That vector F is pointing straight down. Right. So so you can think of that vector F as being its magnitude, right, times this vector, right, that is pointing straight down. All right, so let's make a unit vector that's pointing straight down. Okay, so what's the unit vector in three-dimensional space that's the unit vector in three-dimensional space that's pointing straight down? So its x component would be what? 0. Its y component would be what? 0. But its z component would be what? -1, right? Because you're going down, right? 15. So it's going down. Okay. So now let's see if we can reinterpret this. So this is the same as minus the magnitude of f, right? Times what is this? If you factor out that minus sign, what is this vector better known as? What? K, right? So that's really just K, correct? All right. Now, what I need to fill in here though is what is the magnitude of f? But what is the magnitude of f? You know that, right? Okay, because that is going to be the weight of that's just going to be the weight of the camera, right? Okay. In these vector problems, we represent force as magnitude of vectors. All right. So we know what this force is, that gravity is working on the camera. Okay, that's 120 pounds, right? So here is what there's what F looks like, right? It's just minus 120 times K. So see, that wasn't so bad, right? Okay. Negative because the force is pushing, the gravity is pushing the camera down. All right. That's why the minus is in there. Otherwise, we'd have a camera that's floating upward, right? So and I don't think that's the way it's going to work. All right. Now, however, that force is getting distributed amongst the legs of the tripod, right? So we want to write force vectors that represent the force on the tripod legs, right? Well, there are going to be 3 of them. There are going to be 3 of them, right? Okay. So and so now the book is conveniently labeled points for you because it's going to tell you here in this three-dimensional coordinate system, right, where the tripod legs are located, right? Okay, and also where the camera is located too. I don't know if this is 4 or 4 feet or whatever, but it's some unit of measure, right? Of distance measure. Okay, let's call these vectors so that I don't have to constantly be referring to points here. Let's call these vectors U, V, and W. And so these are going to be the force. How should we describe these? Force on the tripod leg vectors or something. So there are 3 such vectors. Okay, now let's see if we can figure out now what V and W are. Okay, look, if you just look at the picture, all right, if we call this one U, this one V, and this one W, if you just look at the picture, what does it look like U is going to be? I mean, what's its initial point there, and what's its terminal point? Yeah, so you want U going in this direction, by the way, right? Because the force is moving downward, correct? So so what does it look like a U is in component form there? So if you're going from this point to this point, right? So keep in mind they're the coordinates of that point, right? So it looks like, what's the first component of U? 0, right? Second component, be careful now, because yeah, that's right. This is the initial point and this is the terminal point, right? So -1 minus 0 is -1, right? And then what's the third component there? -4, okay? So, I mean, in terms of direction, right? That is the vector U. But now what's the possible issue here with the vector U? Okay, you see the way we wrote u, we can compute its magnitude, right? But the magnitude of that vector has to match, because this is a force vector. So the magnitude of this vector has to match the force on the tripod leg. You see, that's the issue that may not, so this may not be quite correct, right? How would we adjust the, how could we adjust then the magnitude of this vector u? Because the direction is correct, right? There's no doubt u is going from this point to this point in terms of its direction, right? But how could you adjust its magnitude if need be, right? Okay, to match the appropriate force. Multiply by a scalar, right? Yeah, perfect, Elijah. Multiply by a scalar. So the vector u that we're really looking for here, we may have to adjust this by multiplying by a scalar. Okay, that's just my warning. All right, let's see if that turns out to be the case. What about the vector? What about the vector v? This one's going to be messier. So, okay, so v is going from this point again. I'm sorry, going from this point to this point. So, what is its coordinates look like? Not so bad, right? Square root of 3 over 2 minus 0, right? So square root of 3 over 2. Right, and then second one is 1/2 minus 0, so still 1/2, right? And then third one is what? 0 minus 4, so that's minus 4 there. Okay, and then what about for this vector that I'm calling w? So in component form, what would it look like? Almost the same, right? It would be minus square root of 3 over 2, right? And then what, positive 1/2? Is that right? Also? So positive 1/2, and then 0 minus 4 again, negative 4. Right, so there's the vector w. Now, here's the key point, right? Okay, these vectors are supporting the weight of the camera, right? This tripod, right? Okay, is supporting the weight of the camera. So that means then that this vector f has to be the sum of these three vectors. Okay, the sum of the resultant vector, right, which is the sum of these three vectors, has to match the gravitational force on that camera. All right, which we know is correctly represented by this vector. So this vector we're certain is it's correct. Okay, but this one, not sure of, right? Okay, can we check this? So see what I'm saying here is f has to be what? U plus v plus w, correct? Okay. Are we even close to that being the case? What's well, let me put a question mark here, right? What's u plus v plus w there? What is it? So I get what there? Is that 0? And this is 0, that's right. And this is what? Negative 12. Oh, that's close, right? Okay. But just off by a scalar multiple, right? Okay, just off by a scalar. Oh, so to match that, what do I need to do? How do I need to scale then these how do I need to scale these vectors? Multiply them by 10, right? Okay, it looks like that's where we're Just looks like that's where we're off, right? Okay, because when I add these together, right, I need to get this and there. You know, this vector is almost the same as this one. It's just off by a multiple of 10. So it looks like the vector u that we're really interested in here is what? Not just this, but what do I want multiplied in here? 10, right? Okay, so there's really the vector u. Here's the vector v, and here's the vector w, right? And so if I multiply by this scalar 10, right, then this checks, doesn't it? This becomes minus 120 and get the right vector. Now, if that's the case, then how much weight is on each of the, how much weight there is really on each of the tripod legs? So how do we compute there the weight on the force on the tripod legs? Find the magnitude. That's right. Okay. So find the magnitude, right, of each of these force vectors. What is that going to turn out to be there? Let's compute the magnitude of u there. So what does that really turn out to be? So I think I get 10, right, times the square root of what? 0 squared plus minus 1 squared, right? Plus minus 4 squared. 10 times the square root of 17. Well, what's 10 times the square root of 17? Approximately. A little bit more? Oh, okay. So, yeah, the square root of 17 is a little bit more than 4, right? Okay. So, actually, what is it? 40 point what? 41 point. Say that again. 231. Oh, cool. All right. So there's the actual force there on the tripod. So see, slightly different than distributing the 120, right, across the three. Okay. Well, I think if you guys can follow that, read back to this example when you're doing the last two homework problems, that'll help you. But still going to be difficult, still going to be challenging. Look, the thing to remember here is if you have a force which is distributed amongst different pieces, right? Remember, the sum of the pieces has to add up to the force. Okay, right? Okay, so that's what you need to keep in mind when you're doing these force problems. The resultant vector has to be the total force. Okay. All right. Now look, the next operation. So we got 2 minutes here. Let me just introduce what's coming up. All right. So we do have some, as I mentioned, some vector operations are not similar to familiar arithmetic operations, right? And one of those, but very easy operations, is called the dot product, or also called the inner product. All right. So here's how you compute the dot product of two vectors. It's really easy. Okay. You multiply the components and then just add those products together. So if you have a vectors in 2 dimensions and you want to compute the dot product, right, which we often indicate by a dot, all right, that's why it's called the dot product, right? Just multiply the components together and add those up. All right, same thing in 3 dimensions. So if you compute the dot product of 2 vectors in 3 dimensions, you just multiply the corresponding components and add those products up. So it's a very easy computation to make. Look, when you compute a dot product, what sort of creature do you get? So what's the result of a dot product? What sort of output is this from a dot product? This is a what? Is this a vector or is this a number? Yeah. So when you compute the dot product of two vectors, you get a number, not another vector. All right. So dot product of two vectors results in a scalar. Okay. Not another vector. So you might expect when I'm doing operations with vectors, I should get another vector, right? Well, that's not the case here. Here, when you take the dot product of two vectors, you get something that's not a vector. It's just a number. But it's an easy calculation to make, right? Easy calculation to make, and turns out to be useful in certain important formulas. All right. So that's what we're going to do next time. Okay. Well, we're out of time today, so you can leave. Everyone signed the roll. So just leave your name tag. I'll see you Monday. So you can work on your. You can start work. Yeah, you can try to finish your homework right that was due tonight. And those last two problems are the ones that are the trickiest ones. Okay. So who wasn't here today? Marcus not here. Silman not here. Sumamar not here. Okay.